Welcome to part 3 of section 6.1. Here we will be talking about logarithmic functions. In this video, we will learn the definition of a logarithmic function, or log function for short. We will also show how it is the inverse of an exponential function, which is why they're in the same chapter together, as well as explore some of these functions on Desmos and discuss their characteristics such as domain, range, and asymptotes. Let's get started. A log function is one of the form f of x equals log base b of x. As you recall from the second video, if there is no b written, like if there's no base, we assume that it is 10. And then if we are dealing with the natural log, ln, we assume that the base is e. This is what a natural log looks like. Instead of log, it is ln. So this is read log base b of x. This is read natural log of x, or you can literally say the ln of x. A main idea that we need to understand is that exponential functions and logarithmic functions are actually inverses of each other. In chapter 5, we learned about inverse functions and how to find them. So we are going to do a proof to show how an exponential function, when we find its inverse, it's actually a log function. So we'll start with an exponential function of the form f of x equals b to the x. This is an exponential function with a base b and an exponent of x. Remember, exponential functions are of this form where b needs to be a positive number that is not 1. All right, so in order to find the inverse, what we do is we swap x and y. So I'm not going to swap x and y yet. I'm just going to replace f of x with what it equals, which is y. Then I'm going to swap x and y to find its inverse. So we'll have x equals b to the y. Now we want to solve for y. One way that we can do this is by rewriting this from exponential form into logarithmic form, which we talked about in the previous video. So going into logarithmic form will look like this. When we write this in log form, we will know that it's a base b. So it's log base b, and then of x, and that equals the exponent because a log is an exponent. Now we have resolved for y. That means that f inverse, which is our new y, is log base b of x. So when we rewrite this, I'll swap the side, so it's y equals, and instead of y, it's our inverse, since that's what we're solving for. We swapped x and y because it's so to find the inverse, and it's log base b of x. So we have just proved that for any exponential function, y equals b to the x, its inverse is f inverse of x equals log base b of x, proving that exponential and logarithmic functions are in fact inverses of one another. Let's show this graphically with a simple example. In the previous video, we went into depth about how to graph and talked about a basic exponential function such as y equals 2 to the x. Now we know from what we just proved that the inverse, if f of x equals 2 to the x, the inverse function would be log base 2 of x. We just did this proof, but instead of 2, we did in general any b value that works. So let's first graph f of x. I'm going to do this very quickly because we've already discussed how to graph this. All right, I actually did that very quickly. I did it off camera. So I plugged in kind of like the main 7 x values that work just for ease, and raised each one of them, 2 to the x, and then plotted them. So this is what our exponential function looks like. Again, when b is greater than 1, it's an exponential growth function. Now, recall that we learned about the relationship between a function and its inverse. The domain and the range are actually swapped. So this is our domain. Our domain is actually all real numbers. We can plug in any x value that we want. Specifically, the values that I plugged in were these 7, and got these 7 outputs, our range. Now we can see that our range is from open 0 to infinity, meaning that it's only positive numbers that we can output. Well, since it's harder to plug in numbers into a function like this, since we understand the relationship between a function and its inverse, we can actually just swap our x and y values and make a new t-chart like this. In our our first coordinate point that we saw for f of x was -3, 1/8. Well, on the inverse, that means the coordinate point that we would have is 1/8, comma, -3, and so on, swapping x and y. Now I've just swapped the x and y and put them all in a t-chart. I do want to just make sure, just to convince you that this works, I want to just plug in one of these coordinate points and make sure that it does work for our function based on what we know about logs. So I'm going to test out, just going to pick a random one, I'm going to test out this one right here, 1/4, comma, -2. So that means we are going to have an x value of 1/4 and a y value of 2. So we have the function y equals log base 2 of x. I'm just writing y to keep it simple. So plugging our coordinate point in, we should have that -2 equals log base 2 of 1/4. All right, so let's think about that. If we rewrite that in exponential form, we'd have 2 raised to the -2, because the base is 2. Remember, a log always equals what the exponent is. And then that's going to equal 1/4. Is 2 to the -2nd 1/4? Yes. 2 to the -2nd means 1/2 to the +2nd, or 1/4. So this does work, and it's just kind of neat that we can do it in a simpler way with something that makes a little bit more intuitive sense, and then just swap the x and y's. So now that you're convinced, let's plot these coordinate points and see what graphically these two inverses look like. Here is the original exponential function in blue, and its inverse, the logarithmic function, in red. And we can see that they are in fact inverses of one another. Recall that graphically inverses are reflections about the line y equals x. The line y equals x is a diagonal line with a slope of 1 and a y-intercept of 0, so it passes right through the origin. So this graphically, that's what it is. It's reflected about the line y equals x, because literally y equals x and x equals y, right? We swap the variables. So graphically, since we have the coordinate point 0, 1 on the original function, we swap the coordinates and have 1, 0 on the inverse. Similarly, 2, 4, 4, 2, -2, comma 1/4, 1/4, comma -2. So we swap x and y. So graphically, they are reflected about the line y equals x. I want to take a look at some other relationships between the two functions, specifically domain, range, and any asymptotes that we may have, and show how once again they're swapped. So our domain of an exponential function, like this one, that does not have any like plus or minus here, it's not shifted up or down, just a simple exponential function, b to the x here. Our domain, in this case, we can plug in anything. So our domain is all reals, and even if it was shifted up or down, the domain remains the same. The domain is all real numbers. Now our range might be different depending on if there was like a +1 here or -3 or something, if it was shifted up or down. In this case, it's not. It's just a b to the x general exponential function. And our outputs were always positive. So recall the range of any general exponential function was open 0 to infinity. It's open because we never hit 0. We approach it, which goes right into a horizontal asymptote. That horizontal asymptote is the line y equals 0 in this case. We can see that by plugging in numbers smaller and smaller and smaller, since we see we approach it, going to the left. So if we plug in very small numbers of x, we just keep getting 1 over something bigger and bigger, closer and closer to 0. Now our vertical asymptote, we actually don't have one. We can plug in any number for x. So we do not have any restrictions with x here. So our vertical asymptote is that we have none. Take a look at the inverse function, log base 2 of x, and see, you probably already know what's going to happen here. Our domain should be the range of its inverse, because they're swapped. So if we take a look and see, is our domain from 0 to infinity, is our domain only positive numbers? Yes, our domain is only positive numbers, and that is because we can only plug in positive numbers into a log here. We cannot take log base anything of something that's 0 or negative. So our domain is from open 0 to infinity, and we can see that graphically. We just keep getting closer and closer to the y-axis. Our x values are always positive, but never hit x of 0 here or go negative. Now our range following this swap should be the domain of 2 to the x. Is it? Yes, we can look. Our arrows go down forever and up, but also, to the right, up and to the right forever. And so our y values can take on anything. We're going up and down. So our range is all reals. And then we should have a vertical asymptote, but no horizontal asymptote, since those are flipped as well. Well, it does look like we have a vertical asymptote here. Our red graph, our logarithmic graph, is butting up right against the y-axis, and so since our domain, our x can't be 0, that means we're never at x equals 0. This happens to be our vertical asymptote. So our vertical asymptote is x equals 0, and we do not have any horizontal asymptotes here because we keep increasing forever. We're not restricted by any horizontal line. So that is the relationship in general between a function and its inverse, and specifically here an exponential function and its inverse logarithmic function of the same base. This is me feeling like as a teacher I need to show you this. I just snipped this from your textbook, and this is just everything we talked about. Domain, certain points on the graph, everything we really just talked about. We did just do one where the base was 2, so it did follow this general form where our logarithmic function looked of this form. If our base is a positive number but still not, less than 1 here, a logarithmic graph looks slightly different. So really, we have Desmos to take a look at things if we need to. I'm not a huge fan of making you graph a ton of stuff by hand because in this day and age, we don't really need to do that anymore. But just so you know, there are 2 different ways that our logarithmic graph can look, depending on if b is greater than 1 or smaller than 1, but still greater than 0. And that's the same idea between our exponential functions looking different with those same restrictions on b. Time to do a little algebra. We are going to find the inverse of each function. So in number 1, we see that our function is an exponential function. So what we've learned so far is that its inverse should be logarithmic with a base of 3. Let's do that. So the first thing I'm going to do is not really any math yet, but just replace f of x with y. To find the inverse of a function, we swap x and y. And then, because we want to get y equals and y is up in an exponent, we need to go from exponential form to logarithmic form. Before we can do that, I want to get that plus 4 out of the way. So I'm going to do x minus 4 equals 3 to the y plus 1. Now we have what looks like exponential form. I'm going to put this in parentheses to show that it's like one thing. All right, going into log form, we're going to have log base 3, that's our base, of x minus 4 equals the exponent, because the log always equals the exponent. The exponent is y plus 1, that whole thing. I put x minus 4 in parentheses to show that we're not just taking the log of x, but we're taking the log of the whole thing, x minus 4. Now I want to solve for y, so we simply subtract 1. So we have log base 3 of x minus 4, and then a minus 1. The minus 1 is separate. We can't combine this minus 4 and this minus 1 because this one's inside the log, whereas this minus 1's not. So I'm going to simply rewrite, instead of y equals, we'll rewrite it as f inverse of x equals log base 3 of x minus 4 and then minus 1. So that is the inverse function. In number 2, we're starting with a logarithmic function, and it has a base of 10 because we don't see any base written there. We know that the inverse of a log function is in fact an exponential function. So again, my first step, and you don't really need to do this step, I just like seeing y instead of f of x. So the first step is just to replace that. Okay, now we can swap x and y in order to find the inverse. So we'll have x equals 2 log of y plus 3. And now we want to get back to y equals. So now we need to go from log form back into exponential form. But before we do that, I actually want to get log of y by itself. So I'm going to first subtract 3 and then divide both sides by 2. So we'll have log base 10 of y all by itself. Now we can successfully go into exponential form. Doing that, we'll have the base of 10, which remember when we don't see a base and it's an log log, the base is 10. So it's 10 to the exponent of x minus 3 over 2. So that's our exponent, equals y. My last step is going to be just replacing y with f inverse, since it is the inverse, and it's 10 raised to the power of x minus 3 over 2. So we have successfully reviewed how to find the inverse of a function using just our algebraic procedure of swapping x and y and then resolving for the new y. And we also reviewed the concept that exponential and logarithmic functions are inverses of each other with the same base. The last thing that we'll look at with logarithmic functions is something that's important because it's what we can and cannot plug into the function extensively. So the domain is, like with most functions, extremely important. And what we need to understand is that the domain in general is that of a log function is anything positive, so open 0 to infinity. However, that works when it's just like the log of x. But what if it's the log or natural log of something a little more complex, some inside function that's different than just x? Well, in general, what is inside the log or natural log function needs to be positive. So we have to force what's inside this to be positive. So in number 1, the inside function here is 3 minus x. So we have to say let 3 minus x be greater than 0 because what's inside the log function needs to be positive. Once we force that to be positive, we can then solve for x. And you can do this in a few different ways. You can just add x to both sides, or I'm just going to show you, in case you forgot the rules of solving this, if we solved it for x and kept x on the left, we'd have negative 1x is greater than negative 3. Dividing both sides by negative 1 means we have to flip the sign. So x is less than 3. You would have also gotten that had you just added x to both sides. I personally like to keep x on the left with inequalities. So we have x is less than 3, and if we need to write that in interval notation, we know that we can write that like negative infinity up to 3, but not including 3. So that is the way to write the domain there. Number 2 is interesting because we have a quadratic trinomial inside our natural log function. And so what we're going to do is factor it. And so when we factor this inside, we'll have x plus 2 and x plus 3. Now we're not setting it equal to 0. We want to make that greater than 0. And the way that we can deal with this is find the critical numbers here, which what makes the 0, negative 2 and negative 3 make each one of these 0. And we can put this on a little number line and make a sign chart. When we do that, the numbers that we want to put on the sign chart, the ones that we care about, are negative 3 and negative 2. I'm putting them in order, least to greatest. And that makes what's inside here equal to 0. That makes our inside function equal to 0. Now, we don't want it equal to 0. If we plugged in negative 2 or negative 3, we'd get this equal to 0. We don't want that. We want it to be positive. So we need to plug in numbers in this interval in between them, and this interval greater than negative 2, and see what kind of number they give us here. So here's what I'm going to be doing. I'm going to plug in a number to the left of negative 3 on our number line. Let's plug in negative 4. When we plug in negative 4 here, we'll have negative 4 plus 2, which is a negative number. And then we'll have negative 4 plus 3, which is also a negative number. When we take a negative number times a negative number, we get a positive number. Therefore, I'm going to put a plus sign here. That shows us that whenever we plug in numbers to the left of negative 3, we get a positive number inside here. That is desirable. Let's try our next interval, which is in between negative 3 and negative 2. Let's pick negative 2.5 as our number. if we pick negative 2.5 to plug in here, we'll have negative 2.5 plus 2, that's a negative number. And then we'll have negative 2.5 plus 3, that's a positive number. A negative number times a positive number is negative. So that means if we plugged in any number in between these two in this interval, we'd get a negative number inside here. That is not desirable. Lastly, I challenge you to pick a number greater than negative 2, any number, plug it in here and see what you get. Go ahead and pause the video and then hit play to see if you did it the right way. What number did you pick? I'm going to pick the number 1 because it's a positive number. You could have picked any number greater than negative 2. I'll pick 1. So if we plug in a 1 here or a 1 here, we'll get positive numbers. And a positive times a positive is in fact a positive. That means what our sign chart is telling us is that when we plug in numbers to the left of negative 3 and to the right of negative 2, we get our desired outcome of a positive number. If we plug in numbers in between negative 3 and negative 2, we do not get that desired output. We get a negative inside our log. So our final answer is all the places that we get what we want, the positive numbers. That is on the interval from negative infinity to negative 3, and also from negative 2 to infinity. So we can plug in a lot of numbers into this function, but there's an infinite amount of numbers in between negative 3 and negative 2 that we can't plug in. In number 3, we again want to find the domain of our log function here with a base of 3. And whatever's inside here, inside the log function, we need to force it to be positive. So we want to force 3x minus 6 to be greater than 0. So we'll add 6 and then divide by 3. So we have that x needs to be greater than 2, which is from 2 to infinity is our domain. That one wasn't too bad. Then our last one, we have another quadratic. And I didn't mean to put both the quadratics with the natural log. That's how my examples ended up working out. But again, we want what's inside the log function to be positive. So we'll say x squared plus 9 is greater than 0. Now in this case, because we don't have a quadratic trinomial, we don't necessarily need to factor it. We can just go ahead and straight up solve because we don't have a term with x squared and x in it, which makes algebra kind of funky, which is why we had to do this whole process up here with the sign chart. Now in this case, if you think about it, what types of numbers would ever make this negative? None. No matter what type of number we square, it will at least be 0 or a positive number. And then we add 9 to it. This is always positive no matter what. X squared minus 9 would be a different story, and we'd have to do a sign chart. However, if we go and just try to solve this, and if we take the square root of both sides, we end up taking the square root of a negative. We don't need to do all that. So just thinking about this, nothing makes this equal even to 0. And so nothing will make it negative ever. So our domain is actually all real numbers here. Because no matter what we plug in for x, we square it and then add 9. It's a guaranteed positive output here. So that is how you find the domain of any log function. You need to make sure that whatever is on the inside of your log function is positive. If we take a look at Desmos real quick, I decided to put in numbers 2 and 3 into Desmos. Right now we are looking at problem number 2, log base 3 of 3x minus 6. The way that I put this in is I went down here, clicked the little key. I know it looks a little bit different on a desktop, but if you go over to the ABC button, so if we click that, then you can literally type in log or ln, whichever one, and it understands it's log or natural log. Then if you need to put a base in, like here, you can hit this little superscript button, A base B, and then type this in, go back to the 1, 2, 3, and then make sure that you're just not like down there anymore in the superscript. So like hit like this arrow to the right or click it or something like that. So that's how you can enter it in. If we take a look here, our domain we said was open to infinity, and we can see that our vertical asymptote is in fact x equals 2. So we never quite hit that as an x value. So it's only numbers greater than 2 in our domain, and we can see that by the function. So I will now deselect that one and select this one, remember this domain for number 3 was everything except what's in between -3 and -2. So we can take a look at this function here and see it's this cool arc function, and we definitely don't have any numbers in between -3 and -2. We don't have any x values there. So we have two vertical asymptotes, one at -3 and one at x equals -2. So again, you can always take a look at Desmos to make sure that the domain you found algebraically is correct.